One of the things that you learn if you're Joe Hupp's colleague is if you think you know something, you'd better be sure that you really know it. And I thought that we saw perfect evidence for that in Joe's talk. He focuses on things and tries to really understand them at a deep level. Because if you can do that, then you can take that learning and go someplace else with it. He talked a little bit about energy storage and energy capture, and I want to talk about energy storage and energy capture from a slightly different point of view. If you read the interview with Joe that's in the free magazine that you got when you walked in here today, he mentions these perovskites as something that's really going to transform the way we think of solar capture in molecular species. I think that's correct. So I'm going to talk about some older stuff. I'm going to talk about some older stuff because for a while there were two ways that the chemists were going to do this, right? One was dye-sensitized solar cells, and the other was organic photovoltaics. So I'll talk about organic photovoltaics. The reason for that is, in a certain sense, these perovskites are sort of the next chapter, starting from there. Okay. So the work was done largely by Brett Savoy, who is an absolutely spectacular graduate student who we're about to lose. Collaboration with Tobin, with Mike, with Lynn, not with Tobin's colleague there. It's on organic photovoltaics. Going back to one of the real gods of chemistry, Svante Arrhenius. A remarkable man. I think we would not allow him to do this in a lab these days because he's not wearing glasses, but he changed the way chemists think about what they do. He introduced new concepts, new techniques, and new standards. One of the things he got interested in toward the end of his career was actually the influence of carbonic acid in the air upon the temperature of the ground. These days we call that global warming or something like that. And, you know, he published on it in 1896. He was a Swede, so he thought this was great because it was going to warm things up in Sweden, and that was going to be really good, right? But if you want to go back to where this idea comes from of atmospheric absorption, it comes from Arrhenius. Now, the Earth scientists have thought about this in a very different way, and this is the only thing I'm going to say that you probably don't know, and it's actually quite useful. So this is a cartoon of how the Earth's climate system works. So the sun shines, it sends light down onto the Earth. That light can strike different parts of the Earth. It comes into the atmosphere, and the first thing that can happen is it gets reflected out of the atmosphere. So it gets to a discontinuity here and is basically reflected back out, and quite a lot of it is, in fact, reflected back out, mostly in the ultraviolet. If it hits an ice sheet, which is covered with snow, that reflectivity is very, very high, so it comes in and it's re-reflected out, probably at a different wavelength, but nevertheless, re-reflected out. If it hits the land surface, like a coal mine or something like that, this is dark, so it absorbs in the optical and transmits in the infrared. So we've still got emission, but the emission is down in the infrared, and what happens is that hits the so-called greenhouse gas layer, GHG. Now the GHG is there, it's biological, it's geological, it's been there forever, and if it weren't there, this would be a very uncomfortable place to live, because what it does is to raise the temperature by 33 degrees centigrade. Now if you're in Chicago today, the temperature is about -8 centigrade. So if not for that, it would be -41 centigrade. So we like the greenhouse gas layer. But what the greenhouse gas layer does with this kind of thing is to reflect it back, and that warms the Earth. Not the natural greenhouse effect, but this other greenhouse effect. And how do you know that? This is from Jim Anderson at Harvard, who has been really one of the heroes in chemistry of recognizing these processes and what happens. This is actually the Arctic ice. You can see the declines from 79 median here to 2007 here. Jim feels that it's over. The northern ice cap is gone. It's going to be gone in a few years. Southern ice cap is still there, but we've changed the Earth a lot. Does this really matter? Well, you know, I'm very chauvinistic about living in Chicago and stuff like that. So this is what happened to the Chinervia Glacier in Switzerland. This is what it looked like in 1910. This is what it looked like in 2001. It's disappeared, essentially. That's okay. That's a long way away. But it turns out that back in 1909, the chair of the geology department at my institution and Joe's actually named this glacier the Northwestern Glacier. And there it was in 1909, and here it is in 2005. Only here it's not in 2005. It's gone. So yes, we are changing the climate. And you know, this is the standard sort of thing that you get, right? We know that in 1 hour we get more solar energy than all the energy we use in a year, so we ought to be able to do this. At least that's what the chemists would like to think. So I have two vexing questions. One is, how does an organic photovoltaic work? The second one is, how do you collect charge carriers? I don't think we'll get to that. We can talk about how an organic photovoltaic works. Firstly, this looks like, you know, the ultimate Rube Goldberg invention. I have sun coming into this entity. The entity has 1, 2, 3, 4, 5, 6 layers of stuff. So the first thing that happens is it comes into this transparent conducting oxide. Eventually it gets to the so-called bulk heterojunction structure down there, and that's usually a chemical mix of donors and acceptors. So the cartoon is you photoexcite in the donor, and that causes electrons on holes. They separate. The electron goes over to the acceptor, and then through a low work function metal, the hole goes over to the transparent conducting oxide, and you can recombine them, and that's what you do. So you split the photon right there, but you lose a lot of energy. This is not terribly efficient. Why not? Well, firstly, you have to think about how it's structured. This is the same structure that I showed before. The idea is that you have so-called heterojunction, which is to say that there are these two entities, the yellow entity and the blue entity, and they are in that BHJ layer. All the rest of this stuff is to allow the light to come in, to prevent the wrong carriers from being in the wrong place, and to collect the charges at each end. Now let's get to the way it works. This is an energy diagram, and it's really crude. I absorb at that energy. Now if I'm higher, if I'm up here, the rest of the energy just gets degraded to heat. But this is basically excitation from the donor, from the HOMO to the LUMO, I'm sorry. So up here it has to lose energy. It has to have driving force to make it undergo charge transfer from the donor to the acceptor to get a donor-acceptor pair. And that is VOC, the open circuit voltage. So you lose a lot. The only thing you collect is this stuff, which is at VOC. So you lose three things. All the photons below this, which are in the infrared, they don't get absorbed, so they're no good. GCS, this is lost as heat. The charge separation energy is lost as heat. And the cross gap, this VOC, is what determines limiting voltage. So the voltage is not as high as you'd like it. But even worse than that is thinking about this horrible mess that we call a bulk heterojunction. This is a cartoon. The yellow is the polymeric entity. The blue are fullerenes. They could be various fullerenes, but there are lots of different ones. Basically, they're round carbon-containing entities of the kind that we know, but they live in this layer. And the sun has to come in here, photoexcite, and separate and collect. It looks like it could never happen. Firstly, it could never happen because the dielectric constant is really low. One of the things about organics is they don't have high dielectric constants. And that means the electron and hole continue to attract each other. And if you want to separate them, you're going to have to somehow put energy in there to separate them. And that's part of the problem. Now, they do work. How do we generate free charge at all? How do we separate the electron and the hole if, in fact, that's the magnitude of the dielectric constant? And why are fullerenes so good? Lots of different materials have been used for organic photovoltaics, but essentially everybody who wants to get a good number uses a fullerene of some sort. Why is that? Well, I'm a Midwesterner, right? And if I look at this entity, which is the most common derivative of the fullerenes that's actually used, it's PCBM as its initial. That's a fullerene at C60. There's that little thing hanging off the top. And if I look at the geometry of this, what it reminds me of is, living in the Midwest, that's a pumpkin. It really looks just like a pumpkin, right? It's got this big spherical entity, and it's got this hook up on the top. And if you wait until next October and drive through the countryside around Chicago, you'll find these pumpkins all stacked up. Now, when the pumpkins are stacked up, let's look at that pumpkin. It's touching that one, that one, that one, that one, that one, and 3 in the layer below. So this spherical packing is really good, right? Because it allows charge to move from one to another. Because the charges in basically molecular orbitals that are on the outside of this, and yet this is touching all the other ones. So just as pumpkins stack, C60s stack. So now what happens? Well, I photoexcite the donor, which is this thiophene, and I have an electron hole pair. The electron hole pair migrates. When it gets to the interface, right there, magic has to occur, right? The electron has to move from here to here. And once that happens, because these guys are touching each other, this electron can actually speak to all of the other pi orbitals over here, and that is much, much better than any other acceptor. And it works for all the fullerenes, including the C60s and the C70s. And it gets separated because these orbitals are mixed because they're touching each other. Let's think about it a different way. I'm a theorist, and if you're a theorist, you have a couple of things that you believe in, and one of them is the golden rule, right? The golden rule says I'm going to photoexcite from there to there. And as I photoexcite from there to there, I'm going to get to these so-called charge-separated states. Not bound charge transfer states, but charge-separated states. Why? Because I'm going from HOMO to LUMO. Okay, and then this has to charge separate. From S1, which is where I get to, its charge separates over to here. And that's what basically the golden rule tells you will happen. You don't really want to go down here, because if you go down here to these so-called bound charge transfer states, those are the ones I showed you before where there are electrons on holes next to each other on opposite molecules. I got to then tear them apart. That's going to be difficult. It's going to cost energy. And that's what this shows. You really don't want to do that. You have to go energetically uphill. You certainly don't want to do that because it's going to put you back where you were and heat things up. What you want to do is to get it over to here and get it out of there as soon as possible. So this is another cartoon. It's a bit aggressive. I'm sorry about that. You photoexcite from here to here, and when you're in these excited states, great thing about the fullerenes, these acceptors, is that they've got all of this charge density that comes about from the fact that they're packed. They're talking to each other, and so they're delocalized. These are charge-separated states, meaning I've left the hole behind. I've taken the electron over to here. But they're not coulombically trapped because they're in this delocalized region, which only the fullerenes affords. That's what this basically says. So let's compare these two. This is a polymer-polymer blend of the kind that was used before the fullerenes came in, and this is a polymer-fullerene blend. Photoexcitation is exactly the same. Goes from the ground state up to the excited state there and there. But here, it goes to these charge-separated states that come about because of the packing of the pumpkins. Here, these states are lower. And when you get to there, you really can't go over because there are no states here. So you have to go down with the charge transfer, as I show here. And then you're in these coulombically trapped states. And then you have to be activated. So the prediction is that if this proposal is right, this guy is not going to be activated, and this guy is. So the proposal is that it's temperature independent and field independent. It doesn't matter if you're driving it with a field or not. It's basically entropy that's driving this. There are so many states here that that's where it's going to go. It's not going to go down here. It's going to go over to here. Why do we believe that? Firstly, we believe that because these wonderful fullerenes have lots of orbitals really near the Fermi surface, right? So these are the LUMO plus 1, LUMO plus 2 molecular orbitals. They're basically degenerate, and they're all on the outside. So if you're going to touch this molecule, you're going to see a lot of amplitude all over from all these different molecular orbitals that are right there, and those are the ones that are active in the chemistry. So you can do a calculation. You can put a charge here, put a whole bunch of fullerenes together, and find out where the counter charges are. So this is a hole, and that's an electron. This is exactly what we do not want. If it was this, we'd lose, because here what's happened is I've made a local charge transfer, right? But that means that the electron and the hole are still next to each other. Coulomb's law is going to say they're held together easily. May be difficult to get this guy away. So if the states look like that, we lose. But if you look at just the next state, what you see is something quite different, right? This state is a little bit higher, about 0.2 EVs higher, but now it's delocalized way out to here. That's the counterion, but these are where the electronic states are. They're gone away. That's really good. In other words, they're going to get into the sort of continuum that comes from all these packed together polyhedra. Now, it's easy to do this in a really simple calculation. Suppose that you took one of these versus 5 of them versus 10 of them. And you just do first order chemical kinetics, right? dx dt is minus kx. Here, the only thing that can happen is that can transfer over to there and you get charge transfer. Here you get the charge transfer way up here. These charge separated states are far down below. As I add more and more and more of these, they talk to each other. What that does is to favor the charge separated state. By the time you get 10 of them, the charge separated state really wins. The exciton decays and almost nothing goes over to charge transfer. I've won. I've separated my charge, not by putting extra voltage in, but only by the fact that these guys talk to each other, and there are lots of states for the electron to jump into. This is actually work by a guy named Alessandro Troisi, who postdoced with me a long time ago and moved to England and is very smart. Aside, you can tell when a scientist is serious because he gives up the food in Italy for the food in England because he wants to work there. That's a serious thing. So he's a serious scientist. But he did these calculations a couple years back, and these are the states that he computed for these fullerenes. So you can see exactly the same thing I've been chatting about. Really delocalized, really delocalized. Not all of them. Some of them, like this one, are completely localized. But most of them look like this delocalized entity. That's really what's going on in the fullerenic compounds. How do we know this? I've given you calculations. These are some experiments from Richard Friend's group in Cambridge. They're a little bit complicated, but that red line is indicative of what happens in this so-called pump-push experiment. The pump-push experiment is, first you go to the above-gap pump. So you throw in either an optical or an ultraviolet photon, go up to here. That forms this charge transfer state, and it cools. Now I've separated the electron and the hole, but they're next to one another, right? And now if I do a push, which is in the infrared, I can actually now force these guys apart. So there are two categories here. The categories below the red line, categories above the red line. This is the change in the photoconversion per push photon. So if you turn the push on, this guy and this guy really are helped. They go up by more than a factor of 10. All the rest of these guys don't go up very much. In fact, some of them go down. The ones above, these two, are not fullerenic. The ones down here are fullerenic. And the reason we believe that that is true is you don't need to do this push with the fullerenic ones. They've already separated. It's the non-fullerene ones, these guys, that need it. And when you give it to them, they behave much, much better with, factors of 20 or 30. A real example, though, would be really simple. Let's go back to Svante Arrhenius. Let's look at the temperature dependence of these separations. This is a paper by John Asbury and his colleagues that came out last year, 2 years ago. That's what he sees. So he's got these four components, the P3HT, PCBM, which is what we've been talking about. And then he's got these other organic entities that do not have that spherical geometry, which I think is really important. And if he looks at the activation process, what he sees is that if you go to this one, the one we've been talking about, the one that has the buckyballs, it has no activation energy at all. If you go to the one that has these two organic molecules, the flat organic molecules, PDI and P3HT, there you see that it does have an activation energy. So it's activated. Why? Because you need to separate the charges. This is not activated because the charges separate themselves. So it's all in the entropy. Right? The entropy is Boltzmann's constant times logarithm of the number of states. If you've got all these guys jammed together, the density of states gets really, really high. This gets really big. So entropy is driving this. It's not energy that's driving it. It's entropy that's driving it. You've got more states. You fill more states. And the second term can dominate the first, and the exciton can dissociate without energy loss. So their fullerenes are really terrific acceptors. Why? Because of their geometry and space filling. And because of this electronic density all over the surface, and finally because of the fact that they pack together. And non-covalent interactions are absolutely crucial. You can do this with covalent bonding, but it would be awful because you'd have to create these sort of large entities multiply bonded. Here you don't have any covalency. They're just packed together because of their geometry. And I don't think anybody thought about that when they started doing these measurements out in California a few years ago. They just had a few extra molecules around and started testing them, and they saw this very much improved behavior, which we think we now understand. Let's see. Do I or do I not tell you about how to collect charge? Yeah, I think I have time to tell you about how to collect charge. This is really short. All right, so remember back to the cartoon. Cartoon showed that you separated the electron in the hole, and now we have to collect them, right? They have to go through all this collection stuff. We want an analytic expression. Now, for an analytic expression, you have to really simplify. So we go to one dimension. We assume that these lines are just levels, energy levels. And there's site 1, site 2, site 3, site n. There's a sink on this side and a sink on that side. This is an electrochemistry group, so that's the cathode, that's the anode. These guys are going to diffuse, they photoexcite, they move, and they go over and go into the sink. That's what we want to happen. We want them each to go to the right place. We want the negative charge to go there. We want the positive charge to go there. We can model this really, really simply. I mean, really simply because we want an analytic result. So we're going to write a master equation, which says that the change in the number of electrons on site I has to do with flowing from site J to site I. That's that one. If you're on NJ, you can move to site I. That will increase it. Or if you're on site I, you can go to site J. That will decrease it. So these two things are called the master equation. We're going to add two things to the master equation. One is traps. That's what happens with organics. They're not perfect, and there are defects, and that defect can trap, and it can trap irreversibly. So the trapping has a trapping rate constant, and it's proportional to the number. And then there's this input from exciton breakup. We're continuing to break up the excitons, so we're adding more charge, so we're getting increase with N with I. That's the equation we want to solve. It's a first-order linear differential equation, and it can be solved exactly. So Brett was very proud of himself. He went through all of this applied math, but effectively, the minute you see an equation of this kind, you know it can be solved exactly because it's first-order and linear. And these are the solutions. They're nasty-looking, but they're closed. They're closed form, so they're exact. So we can go to drift and diffusive collection. What's the difference between drift and diffusion? Well, in drift, you put a huge field against this, and you drive them. Drive the electrons in one way and drive the holes in the other way. In diffusion, you don't have an electric field. They just diffuse. And, of course, what can happen is they can go to the wrong place. Here, you really want the hole to be here, but maybe the electron would be there. And some of those layers that we saw before were put there exactly to take care of that problem. Okay. And then you can put a barrier. That's what I was talking about. You put a selective contact. You put a barrier here which will only allow the electrons through. If the holes come here, they can't pass the barrier. And Tobin Marx has done a lot with that because it actually helps quite a lot in non-fullerene behavior. So as, again, you have this really nasty-looking mathematics, which we will not worry about. But they look like this. So this is the electric field. When the electric field gets really big, you're in the drift regime. When the electric field is really small, you're in the diffusion regime. This is for selective contacts, blocking. This is for non-selective contacts. These are much cheaper. What you can see is that if you're in the real drift regime, if you're really hammering these electrons on holes with a big field, it doesn't matter. These things look exactly the same as those. But if you're in the diffusive regime, then doing the selective contacts is tremendously helpful. That's 0.6, and here it's about 0.1. So it's a factor of 5 or 6. So this really, really helps if you don't want to put in these blocking layers. Then you're going to have trouble down here, so you need an applied field, and that would put you in the drift regime instead of the diffusion regime. And that's what all of this says. So this brings up a question, which is why do we still make thin devices? None of these are very good absorbers. If we made them thicker, they would absorb more light. We don't make them thicker. Why don't we make them thicker? These are some calculations that Brett did on this material, the sort of standard material. What you see is, with low trap density, you optimize up here at about 5%. That's high thickness. That's 200 nanometers thick. But if you have high trap density, by the time you get to 200 nanometers, you've lost the peachy region. You've gotten into the bad region again. Right? So if you have high trap density, you can't really make the thing very thick because all your charge is going to trap and you're not going to see anything. Which says, basically, that at low trap concentrations, thicker devices are desirable because they can capture more light. But at moderate trap concentrations, thicker devices are no longer desirable because of this trapping probability. And that might explain the reason why essentially everything is still quite thin and we don't capture all the light that we could. We have a break now. I just wanted to show you this picture. You've all seen this picture. I love this. In 71, I'm never getting off that sphere. I don't think anybody else in this room is getting off that sphere. The other thing, your son was born day before yesterday. He may be able to do it. He may be able to get off that sphere. But for the rest of us who are living on that sphere, we have to take care of it. When the astronauts took these pictures, they all came back with the same kind of remark. The Earth was a beautiful blue ball in black space. We have to do our best to preserve it, and I think as a chemist, the idea of using photovoltaics to try to help this along is really a very